Oh wow. Interesting. First of all, I'd like to thank the organizers of this event for allowing me to come and present. We actually worked all night trying to compress the slides I was supposed to show today. Initially it was 30 minutes, and then I was told to compress it to 15 minutes, but now I've just been told to compress it to 10 minutes. How we're going to do that, I don't know, because I'm supposed to talk on complexity. The word itself says a lot. Okay, so my name is Abiodun Shonibare. I studied architecture at Covenant University. I did my master's in environmental design at University of Lagos. And then I have a master's in parametric design in architecture from the University Politecnica de Catalunya in Barcelona. I'm an architect. I'm a member of the Nigerian Institute of Architects. I'm registered with Archon, and I'm also a member of Interior Designers Association of Nigeria. I'm an associate partner at Studio Stone Designs, where I practice core architecture. And then I'm the director of ShiftFlag. And sometimes people tend to get confused. How come you're working in two companies? Well, ShiftFlag was actually an R&D department of Studio Stone Designs. We got so busy that we had to separate it and make it a separate entity. And I'll explain further. So basically, I'm an architect, computational designer, and entrepreneur. If you want to reach me, you can reach me on LinkedIn, Abiodun Shonibare, or arc_Shoniboy on Instagram, or Studio Stone, or ShiftFlag. I'm very active on all platforms. Next slide, please. The way in which a problem is decomposed imposes fundamental constraints on the way in which people attempt to solve that problem. Rodney Brooks, 1999. Next slide. If I was to tell you to make a cube from a sheet of paper, basically from our elementary training, you literally just get a cutting knife, either cut a crucifix and then fold and assemble. Next slide. But if I told you to make a cube from a log of wood, you tend to have a constraint on which particular type of tool you would use. Would you use a chisel? Or if you're more, I don't know, digital savvy, would you use a CNC router or use a circular saw? It depends. But the constraint, the problem gives you a constraint and that you have to solve. A tool for solving those constraints is algorithms. And what are algorithms? An algorithm is a precise rule or set of rules specifying how to solve a problem. Next slide. An algorithm can be likened to a recipe. If you want to make a brownie, you literally need some ingredients that are displayed. Maybe a cup of butter, teaspoon vanilla, cup of sugar, unsweetened cocoa, eggs, flour. And you have to follow a certain procedure to actually make the brownie, because you cannot start from number 7, which is to microwave what exactly? You need to start from when you melt the butter, mix it with the sugar, mix the other ingredients till you get to item number 7, and then you get a brownie. Next slide. But that particular algorithm I showed you doesn't tell you how to make a cake like this. Next slide. Neither does it tell you how to make a cake like this. There's something missing in that particular algorithm. Next slide. And that is using a 3D printer for digital fabrication to actually create a mold to actually be able to bake a cake in a certain particular aesthetic quality. Next slide. I'm a big fan of the Matrix, and I always use it in all of my presentations. You all have the conscious choice to understand algorithms. So just like Morpheus gave to, I don't know if you've watched the Matrix, you know about when he offered Morpheus 2 tablets, the red pill or the blue pill. The red pill, you embrace algorithmic thinking and unlock the plethora of opportunities that comes with it, or you take the blue pill and you just fade away, literally. Next slide. What is complexity in architecture? To the left, you'd see a regular rectangular building, and to the right, you see a fluid type of building. The fluid building is complex in the sense that it is difficult to execute. But for somebody like me that has dabbled into computational design, I see that fluid building and I just see a finite number of rectangular blocks that were actually arranged to create that fluid building. Next slide. And in order to be able to achieve that, I literally just screen grab a particular lecture I did in school. computational design. Computational design involves computational design thinking, which has to do with logic and asking the right questions. And luckily for us, most of the speakers that or the people that have spoken before me actually were able to answer, especially Dr. Z. He was able to cover a whole lot of things, so I won't probably dabble as much as I wanted to. But the questions are: can we do stuff faster? Can we automate? Can we is it possible to work with a different workflow? Is it too manual? How can we optimize? Can we create our own tool? Can we do it more sustainably? Can we even move from one particular software to the other, which was what one of the speakers said. Those are the challenges in the AEC industry. And then with computational design, you begin to question yourself like, okay, what is really an architect or what is really an engineer? Because at some point you start to find out that the line is being blurred, and I will explain with a particular project. Next slide. Okay, so why computational design? The traditional workflow. Sorry, I'm an architect, so I'll just use that particular angle, right? The traditional workflow is to do a manual drawing, and then sometimes, if changes are required, you'd have to redraw, and then that takes time. In this capitalist society of ours, time is also money. You need to be able to manage your time properly. But with a parametric workflow, you generate an algorithmic model, which allows you to adjust parameters. This is a video, Elijah. So if you could just play. No, previous slide. Sorry. Yeah, there's a video there. So if you can just play. You can't play. You can't play. Anyways, um, on the left, there's actually a slider. Once you move those sliders, you can actually fold the angles of of this particular facade, or you can extend the length or reduce the height. You can do different things with this particular model in seconds because it was made parametrically. This actual script was used to make a particular facade we did for InterSwitch, which I will show you later on. Next slide, please. Um, and the tool itself is called Grasshopper. It's it's is used to create algorithms without coding, in the sense that you don't need to learn some types of syntax. Like for instance, C sharp will tell you to always have a semicolon. I guess I'm not sure if it's C sharp or Python. I tend to get mixed up, but whenever I'm on that IDE, I tend to know what I'm doing. But I mean, with Visual Studio now, it sort of helps you to you don't need to worry about the semicolons or anything like that. But then I don't know if you're just like me. I wasn't taught programming in school, so to start delving into such a thing, you can find it a bit difficult because it can be a bit abstract at the very beginning. But it's actually an essential skill to pick up, and a very good way to transition into programming is using Grasshopper, because it's a visual programming language, i.e., it's more of the user interface is not, you don't just see lines of codes and you don't know what you're doing until you press play and then you now see the results of the code. Rather, as you're actually changing, you're simply just connecting nodes. And as you're changing sliders, you're seeing the results. And this script literally just says, oh, create a grid of points. And at those grid of points, create circles that are 13 mm radius size. That's all. Next slide. So I'm just going to talk briefly about a project I did in school. It's called the Pentaora. Penta means five in Catalan. I don't know what the aura means. I've forgotten. But basically, the pseudocode on the left is the pseudocode. Basically, we just created line typologies, created a mesh structure, did a dynamic relaxation. In architecture, there's something called form finding, where you use natural forces to be able to create a particular type of geometry. So former like old architects like Fry Otto, Heinz Hansler, and Anthony Gaudi, they used to use this particular method. But right now with Grasshopper, you can actually do a digital simulation of form finding, and that's what we did on the third line. And then obviously when it comes to shell structures, they're quite aesthetically pleasing. They don't use as much material as other types of structures, but they can be difficult to actually build. And so we had to make them, and they also, when it comes to point load, they can be very weak when it comes to point load. You need to distribute the forces evenly. So we had to first of all make it corrugated in the sense that when it comes to roof structures, when it comes to roofing materials, and this was something I just learned, your roofing material is actually corrugated because you it comes slender, right? It comes as a very thin sheet, and you can bend it. But when you corrugate it, it actually becomes rigid. So when rain falls on your roofing sheet, it actually doesn't get depressed, and that's why corrugation is good. And so we had to corrugate it because it was designed for primary school, and we just assumed that or part of their safety in the building code was to assume that people might actually want to climb it. So we had to make sure it was safe enough for students to be able to climb. Lo and behold, people actually climbed it. And then we did fundamental analysis. So basically, the parametric model was so flexible that we could actually increase the corrugation within seconds. We could pinpoint, we could do some analysis like utilization factor. We could determine how the angles of the metal joints that could actually hold the place together. Sorry, I'm just trying to rush through this thing. Um, so if you were to do this thing manually, like if you had drawn the physical model, if you had drawn the model, maybe with AutoCAD, and you want to try and get the angles between each plate, we're having over about 320 boards here. So therefore, a connection of maybe a triangle to an edge of a triangle to another edge of a triangle. So you're probably having like 150 metal plates joined together. Sorry, what am I saying? It's a triangle, so it has three edges. So that's 450. So that's like 300%. Like imagine just having to calculate the angles of every single thing. But with Grasshopper, you can actually get data, and just work with the data. All I'm just saying are lines of code, literally, and it just allows you to be able to manipulate data easily. Next slide, please. But with Grasshopper, we could actually do blowout models, details, nesting. So nesting optimization, we had a particular budget of about 15,000 euros, and so we had to ensure that what we were building was within that budget. The initial design was quite huge, so we had to optimize it using a nesting algorithm to reduce the number of materials we're going to use. Next slide. And basically, yeah, at the bottom left are the kids that we assumed were not going to climb. But yes, you can see them climbing. So, but it was good that we designed it for that particular. This is supposed to be a video. I don't know if Elijah, can you play it? This was just to show the script of how it works. If you can't play it, we can just move on. Let's move on. Next slide. Next slide. Okay, let's come to Nigeria. Yes, so shift flag. We do a lot of design, and we provide services. We render computational design services and fabrication to different individuals in the AEC industry. And some of our works, you might have seen them and not known that we actually did them. So I just said, okay, let's just present them. I don't know if you've been to Roxton Street Herald Play. We did the ceiling design for DHK interior designers. The fence design is actually is for a private residence in Banana Island. I'll talk more on that. We've done a bit of R&D on thermoforming. There was a particular facade. The man he had a particular complex geometry which couldn't be developed, which we couldn't make through developable surfaces. And so we had to explore thermoforming options, which actually came out right. We do a bit of product design. This pavilion was done somewhere in Dolphin using bamboo. There's a facade that we did for InterSwitch. We collaborated with the architects Black Country. It's on Okawo Street, Victoria Island. And then obviously we do a bit of computational design workshops as well. Funny enough, I think three of the guys in that picture are no longer in the country, which is quite funny. Next slide. Okay, yes. This was supposed to be, there was a video here, but I know we can't. The video was to show, okay, so this particular fence, it had different design options based on the architect's preferences. And the options were being generated based on cost as well. So as he was changing it, this was supposed to be moving so that you see the interaction. Anyways, the point was based on his changes. Oh yeah, can you imagine? Yeah. So based on his changes, the lengths of the steel pipes that we're purchasing were changing, and you could see the actual real time, cost of all his design iterations. And then we were also getting the fabrication drawings automatically as well. Next slide. With Grasshopper, this is also a video. With Grasshopper, I've been able to also delve into robotics. You can play the video. It's a video. Yeah, yeah. Thank you. So this robot, this is a KUKA robot helping me to like an assistant in doing welding an arc. I had to learn superpose. I mean, studying Grasshopper has been very good to me because I've been able to delve into different professions as well. And then on the left, the potential for using robots in architecture. These are two robots working in collaboration together at ICD Stuttgart in Germany. Next slide. Okay, skill set required. You need a curious mind, obviously. Next slide. Just it was supposed to be like an animation thing. Sure, you get. You need basic knowledge of math. That is logic, trigonometry, and linear algebra. Like all those differential calculus they taught us back in school, and you thought, oh, they were useless. At some point, when you start using programming, you start finding out that you really need to know the derivative of a curve or stuff like that. Next. So sources to learn from. It's yeah. Keep moving. Next. Next slide. Okay, you can go to Rhino Forum, YouTube, Vimeo. It's quite sad that I can't mention any Nigerian institution as some of the speakers had said. Previous slide. I'm still talking. Sorry. Previous slide. Okay. But you can go to thinkparametric.com, how to Rhino, parametric architecture, even Shiplag. Sometimes we do workshops, and while we're doing the dry run, I was told to announce that if we're doing a workshop, we'd give a discount. I don't know if that's still okay. I'm pretty sure the organizers would announce that later on. Next slide. Conclusion. Before I read that, there were some things I wrote down. So yes, I mean, people are no. What? I'm still talking. Conclusions. Yeah, just stay there. Thank you. Um, we were talking about the brain drain. I mean, I know a lot of people that tend to like move to Canada. In fact, like my set alone, maybe they did my secondary school reunion. My guys, including my principal, they did reunion in Canada, and I'm here. But anyways, it's just funny that at the moment, Shiflag is actually working on a project in Canada. So we're actually designing something and we're shipping something to Canada, which is quite nice. Um, uh, there was something Dr. Z mentioned, and I would like to treat it very well. Fail fast, and fail quickly, then learn from it. There are a lot of things. I mean, because of the kind of things we've done, we've gotten our hands burnt on certain types of projects. But I mean, it's made us better than we were before. So I guess it's also you just attempt to do stuff and then you learn from it as well. Um, it would be nice if I would also just like to reiterate and thank God one of my lecturers is here for Unilag. I'd like to reiterate that they actually incorporate computational design into the syllabus. I mean, it will go a long way because that pavilion that I showed, maybe like because me, I'm a typical Niger guy and I've literally held a hammer before. There were some people that they've never actually held a hammer, but that building was literally done by we were just nine students. We designed it, fabricated it ourselves, and assembled it ourselves with no help from anybody. So it just shows the potential. There are so many things we can do. And yes, Dr. Z had mentioned something which I would like to also reiterate. It's funny how it's even difficult to start using AutoCAD in our institutions. Whereas when you're forcing the students to, do hand drafting and all, I mean, it's good, but I think if you want people to give you different results, you need to do different things. And so I'll just end with this particular quote. Just as there are others that dogs can smell and we cannot, why then does the remark, perhaps there are thoughts that we cannot think, surprise you? Evolution so far may possibly have blocked us from being able to think in some directions. There could be unthinkable thoughts. There are certain types of designs you cannot do without computational design. Literally. I mean, it's just like you can't predict the weather by just looking, except if you have some spiritual analysis type of thing. But with computation, you can use data and then you can predict. You know, and that's why I just conclude myself. And computational design can help us break that barrier. Thank you.
Thank you. Thank you so much, sir. We truly appreciate your insights. I mean,